Alrighty, this was requested to look at circuit analysis worked example 9.1 from the textbook, page 252, which I think I've changed what I'm asking for based on the actual question, but I'm using the same diagram. So essentially we're looking for A1, A2, and voltage, remembering A is amps, which is current. So here's the plan. And also on the lesson there was this full worked example, but we'll kind of talk through it because looking at it just like that, it gets a little bit crazy. So let's take a look. So first things we're going to do, I'm going to zoom in here, let's see how that works. Beautiful. First thing we're going to do is basically we're going to find the total voltage. And this is, for this example, it's quite simple because it's given to you. Total voltage is the voltage in this circuit, put into the circuit, which is right here in the battery. Right, so our total voltage for this circuit is just 12 volts. So that's quite simple. So we got 12 volts. And what we're going to do is basically, because that's total voltage, we're going to call it VT. We're going to have a couple of other V's, but we're just going to call it VT. There it is, total voltage. So since we have the total voltage, we can now, next need to dive in and find total resistance. And this is where we're going to use Kirchhoff's two laws. Basically not necessarily his two laws, but basically how voltage works in a series and parallel circuit. So we are going to first we always look at parallel before series. So if we look at R2 and R3 are actually in parallel with each other, so there's a circuit here and that one there, we're going to ignore our A1, A2, and V, all that. We're going to ignore that for now. We need to do this first. So first we're going to look at parallel, so I'm going to call this RP. RP, okay? And in this case here, basically, because it's parallel, it's 1 on RP is equal to 1 on R2 plus 1 on R1. So if we look at basically kind of a parallel, that actually looks like this. You can go 1 on R2 plus 1 on R3. And in the end, we end up getting 1 on 10 plus 1 on 10. So 1 on 10 plus 1 on 10. Okay, and so therefore our RP is 2 on 10, which then just equals 1 on 5. We have to remember that's 1 on RP. So if that's 1 on RP, then basically RP must be just 5 ohms. RP, so we're going to take the inverse, equals 5 ohms. And I use P just because it's my parallel part of the circuit. So you can call that anything you want. I call it RP. So this is 5 ohms right there. Whoop, there it is. If we take a look down here, that's exactly what I did at this point right here. So 1 on R, I called it, looks like, is that XY? I don't know what I called it, 2, 3. I don't know what I was doing there, but that's all right. It's the same thing. R2, R3, 10, 10, 1, 5. And so we get 5 ohms as my total. So now that we have that, technically what we've done is we've actually taken these two resistors, smushed them together, and made just one straight path across with a resistor in the middle that is 5 ohms. So we've kind of created this boom, boom, right across. Right? And we've kind of created this 5 ohm resistor right in the middle. So now that we've created that, we can actually ignore this parallel part of the circuit, because now we actually have a circuit that kind of goes around like this, around like that, through this basic kind of this combined circuit, which is basically now parallel, series, and goes around and back in again. So because that, we can now use, basically we can say, well, our RT, our total, because now we only have a series circuit left, so we're going to call it RT now. And since it's in series, it's just R1 plus RP, right? So this was our RP. And so we have R1 is 20. Our RP was 5 from previously. So we end up with basically 25 ohms 25 ohms right there as my RT. If we scroll down again, take a look, we'll see the same thing. RT is equal to R1 plus RXY. RT is equal to 20 plus 5. RT is 25. So that is our total. So there is find total resistance, parallel first, then series. And that's what we've done here. So we know we have our next one there. So we actually have RT equals 25 ohms. Okay. Oh, what did that do there? Alrighty. So the next thing on our list that we suggest we do is basically find the total current across it. So we're going to use Ohm's law. Okay. But we have VT. We've got RT. So Ohm's law, if we kind of go back to our previous lesson here, I'm just going to dive back to actually, so we go back and take a look at our Ohm's law lesson, and if we see Ohm's law is given to us as R is equal to V on I. So that's what we're going to be using. So where was it? There it is. Let's try this. There we go. R is equal to V on I, so Ohm's law is R equals V on I, so that's Ohm's law, nice and easy. I like using kind of like this I like that, so that's basically I don't confuse with a 1 or anything like that. Alright, the only thing is basically we know that basically we are looking for, we have RT, VT, and we're looking for IT. So if this is RT, this will be, and this is VT, that means this is automatically going to be IT. So that's what we're going to be using there. So we have basically RT is, we just do a quick little rearrange. We got IT equals VT on RT. And we got I then equals 12 on 25. Right, and I just don't have a calculator beside me, so there it is. 12 on 25 is equal to 0.48. I equals 0.48. Whoop, that's a horrible 8, but let's move that. There you go. 8 amps. 0.48 amps. Okay, and so that's IT. Sorry, there it is right there. Okay. Find the total current. So we have total current. There it is right there. So IT equals 0.48 amps. And I really dislike that ohm symbol. So I'm just going to fix that very quickly. Much better. Alright, cool. Now we have that information, we can find the voltage drop across each resistor, right, which is basically going to help us find a few things. So, first things first is we have to kind of now remember Kirchhoff's current and voltage laws. Alright, so if we have here straight away, basically IT is, so A1 right here, 0.48. So we got to remember that across this circuit, in a series circuit, which basically if we put these two here together, it becomes a series circuit. Our current stays the same. So our current here is the same as our current here, which is the current here, which is the current here. Okay? And what ends up happening is current's coming through. Current will split between these two, 1, 2, and then it'll come back together and it'll be the same here. So what that means is that basically our current right here, where it comes out, is going to be the same as A1. So that means IT is going to be A1. So that's where this kind of came from. So this here is actually, so IT is also going to be A1. A1. So that's what we're going to measure there. Okay, so there we've actually solved A1. A2, so now it's basically looking at, again, basically we got our current laws. Current laws say current is going to be coming into here at 0.48, but then it's going to split there and there, go across the two basically parallel resistors, and then come back together, and then become 0.48 going out. So coming in, if that's 0.48, and this is R2 and R2, sorry, R3 and R3, that means basically kind of, in this case here it's nice and easy because it's 10 ohms and 10 ohms, so they're perfectly even, so our current is going to split perfectly over these two. So if 0.48 is a total current, that means basically this will be 0.24 going this way and 0.24 going this way. Alright, so we can know that when it's like this, but what I'm going to do is I'm going to kind of pretend that I don't know that, and that these two are potentially two different resistors instead of 10. So what we're going to do is we actually need to figure out our voltage drop, because even though current splits in a parallel circuit, voltage stays the same. So our voltage coming out here is 12 volts. It's going to drop a certain amount over R1, come down here, hit here, and whatever that drop is, whatever it is in this section here, it'll actually also be the same in these two sections. And because it's the same in these two sections, I can figure out the total current on these two. So we're going to figure out our voltage drop here at R1. So we're going to go over, and we are going to go basically kind of V. So V1 is equal to R1 times I1. So this is just rearranged Ohm's law. Okay, we're given our resistance is 20 ohms, and our current, because this is in series, our current is going to be 0.48. It's just going to be IT. So you got V1 is equal to 20 times 0.48. So V1 equals, so, and I think I've done that down here, V1, 9.6, no, that's not correct. Alright, darn that, I'm going to have to pull out a good old calculator here. 20 times 0.48, 9.6. Alright, 9.6 volts. So what that's saying is that that is our voltage drop. Okay, so that's how much voltage this R1 is using. So if we got 12 volts coming in here, and it drops by 9.6, coming down to here, it's going to be 12 minus 9.6. Okay, and they've got, there's V1 is equal to 9.6, they've got that right there. Okay, so that's what we're going to do. So we actually have, what we have is 12 minus 9.6, is basically 2.4 left. So that means basically we've actually got 2.4 volts right over here coming into this parallel point of the circuit. And from Kirchhoff's laws, we know that voltage stays the same in parallel, right? So that means basically this will be the 2.4 volts. This will also have 2.4 volts. So we can actually now do that with R2. We can say, well, R2, so I'm going to Ohm's law again, R2 is equal to I2, which we don't know. V, the 2.4 on I2. Right, R2 is 10, 2.4, so we end up with, basically if I rearrange this, we got I2 equals 2.4 on 10, right? And we end up basically 2.4 divided by 10 is 0.24. So we got I2 equals 0.24. And notice how I said before that the current splits between these two. So, and because they're both 10 ohms resistor, the current will split perfectly evenly. And so I have 0.24 going this way, 0.24 that going that way. Our math checks out, and we get basically 0.24 amps going there. So that means basically as we're going from there to there, we're actually hitting right here, that's 0.24. And so that would be our A2. Here's what this is going. A2 is going to show that. Okay. And lastly, we need to find V. So we need to find this one here. So we're actually measuring from there to there. Okay. So we've actually already done all our math that we need to do for this. because we figured that basically we've got a 9.6 volt drop here, so basically V1 equals 9.6 volts. Oh. Okay, and with 12 volts here. And the way the circuits, we kind of pretend the circuits work is that basically kind of as they go around and around and around and around, as they go out, there'll be 12 volts, and as they come in, it'll be 0 volts. Everything is used up. Every single bit of voltage is used up. So if we're actually going along here, we've used up 9.6 volts over here, and then from there we can see that our voltmeter actually connects here and here, so it connects across these two, so it sees these two resistors as basically the same. So what that means is that basically kind of on this side here I got 2.4 volts. On this side I've got nothing else to use up any voltage, so on this side I have to be 0 volts. So basically the difference between the two, 2.4 and 0, is 2.4 volts. So this voltmeter is going to read 2.4 volts. There it is. So that voltmeter is going to read 2.4 volts is what it's going to read. And again, we got to remember, basically with Kirchhoff's laws, that's basically kind of across a parallel circuit, voltage does not change. So that would be 2.4 volts will be read there, 2.4 volts will be read there. And it doesn't matter if this is 5 and 20, it'll still be 2.4 and 2.4. There's no change in that at all. And so therefore when we measure on the two ends of it, we're going to just read 2.4 volts. And that gets us everything we need for all this answer. So we get basically kind of VT is 12 volts, RT is 25 volts, IT is 0.48 amps, which gives us basically 0.48 amps as our A1, 2.4 volts as our V, 0.24 amps as our A2. We're going to do a few more of these, so next week. So when we do our circuit analysis section here, we're not going to analyze that, it's just silly. We're going to go down here, we're going to do some analysis of this circuit, which is a little bit more intense than what we've done before, and we've also got 2 other circuits to work through as well. So we're going to do lots of practice on this, and hopefully that will get you where you need to go. Thank you. Bye.